Hey, all you math Padawans, it's time to dive into probability. Are you ready? Here we go.
So we're back to probability, and today we are going to be looking at a couple of things. We're going to be looking at empirical probability, and we're going to compare that to the theoretical. I'm also going to add in a little bit of talk about dependent events and some tricky situations involving and or. So empirical versus theoretical, and also I'm going to look at a little bit of dependent events. And we're going to start talking a little bit about and or, because those are going to be some of the more, I find, interesting questions. Now, probability is you guys your basic stuff, like you roll you pick a card out of a deck, what are the chances? But you also have things like, what if this happens? But there's also this little bit of situation. So I don't know, some fun stuff. But let's just talk about empirical and theoretical. So theoretical is what should happen. Just think about it this way. The most easiest way to think about it is you flip a coin 10 times. What should happen? What do you think should happen? I mean, a coin only has how many sides? Two sides. So the chances of every single time you flip it is 50-50, right? So if I flip it 10 times, should I get five heads? And should I get five tails? Well, empirical is actually what happens. So what actually happens? So imagine you actually do these experiments. So that's what we're kind of looking at, and just understanding that these two things are different. Because life is not basically the perfect theoretical assumptions. We have different things that happen. And that's why we have to go and test things. Test, 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 test. And this is just kind of, your life lessons and that sort of thing. Should you only test once? Or should you test many times? And what is many? And what is a good number for many? So for instance, back to your flipping a coin. If I flipped a coin once and I got a head, you got heads. Could you stop right there and say, well, every time you flip a coin, you get heads? Look, I did the experiment. Every time I flipped it, I got heads. Wow, okay. Well, if you did that multiple times, I think we all know that you wouldn't get heads every single time. It'd be crazy if you did. So how many times do you need to do it? As you go into the real world and you start thinking of different experiments, you have to ask yourself, how many times do I need to do this to prove that it actually does happen? It's not just chance or luck. Questions to ponder. But if we actually just looked at this with I don't know, a spinner. So say you had a spinner just pop up all of a sudden, and you had these six colors. And I asked you, what's the chances of getting a color? Well, you would have your theoretical. This is what should happen. That wasn't very good. There we go. This is what should happen, right? Almost 17% of the time you should get each color, right? But let's just say I went and I spun it, I don't know, let's say I spun it four times. Boom. And this is what happened. Look what happened. Twice I got yellow, and twice I got the color of cyan, which I love. It's that kind of that light bluey, turquoisey kind of color. And there you go. So I never got red, I never got purple or lime. How many times do you think I would need to spin the spinner in order to get closer to the theoretical probability? Well, this is what I want you to know. So the more tests you run, the more events that you do, it gets you closer to the theoretical. And this is where scientists have to make up their judgment call, is how many times do you need to run things to say that, you know what, we're good. We've done it enough times. We're pretty confident this is what happens. So this is always the kind of I guess the real dilemma for scientists when they're doing things. And it's why it takes so long to have things proven, because we need to do things repeatedly to make sure that it wasn't just chance. So we want to talk a little bit about that. So a little bit of theoretical versus empirical, which is always good. But we also want to go and let's get rid of those and get rid of this. We also want to be talking about a little about some actual stuff, some actual math. So remember our probability of our events. So the probability of the event is basically is equal to the number of ways. I mean, I've said this lots, right? Number of ways divided by the number of possibilities. So number of ways to get something, the number of total possibilities. And basically, we're going to kind of play off that a little bit today. We also talked about independent events. So independent events are where things don't really impact things. And that's where you're going to be basically kind of multiplying your different events. So I'm saying the events are A and B when you go and multiply them. And sometimes you can have dependent events that things are dependent upon. So you have to be kind of careful. So I'm going to give you some examples, and we're going to go and let's use a drawer of clothes. Should we use a drawer of clothes? Yeah, sure. So example. You have a drawer. I'm going to say socks. Of socks. All right, you got your socks. I love cool socks. And you have 3 Star Wars socks. And you have 4 pairs of Marvel socks. Okay. So if I just asked you, so here's a bunch of different questions, right? So you can use this situation to ask a lot of different questions. So we'll use this. You have a drawer of socks. You got 3 pairs of Star Wars socks and 4 pairs of Marvel socks. So like number 1, so what you say like, what's the probability of choosing a Star Wars sock, right? Well, so how many ways could you choose a Star Wars socks? You say that's 3. And how many total possibilities were there? There were 7. So that's just 3 out of 7. But let's get into the more kind of interesting things. Let's go up here. What's the probability of choosing Star Wars sock followed by a Marvel? Now, it's really important that you pay attention to the wording in probability questions. So this was followed, and I want to highlight something that was not written, that there was no replacement. So you always have to be thinking about, are we replacing things? Because if you replace, so if I had chosen that Star Wars sock and then put it back in the drawer, things would be different. But this one has no replacement. So ask yourself, does the first event, choosing a Star Wars sock, is that going to impact the second one? It is. That's going to be dependent. So it's dependent upon that happening. So we say this. This is what we write then. So this is going to be a dependent question because the first impacts the second, right? So this is dependent. And we have some funky way to write this. We're going to say this. I need some room. I need some room for this one. We're going to say the probability of A, so the probability of choosing the Star Wars sock, times the probability of B, this straight line, which means given A occurred. So this means B given A. Given A. Okay, so what actually is it? So what's the probability of A? So choosing a Starburst sock, we just did that one, right? So 3 out of 7. What's the probability of B happening given that A just happened? I chose a sock. Woohoo! How many socks are remaining that are Marvel? 4. And there are 6 total socks now, though, right? Because you lost a sock. So what's the chance of this happening? It's going to be 12 out of 42. So almost a quarter, almost 25% of the time that's what happen. Just about that. So really be asking yourself, is there going to be replacements? Because replacement is kind of the key word for a lot of these kind of things. And you're kind of going and just basically multiplying things. Does that make sense? Cool. That's a fun one. That was a fun one. Let's get into some more interesting ones. I know this is super small. Okay. So here we go. So this is going to kind of kick it up a notch a little bit. And we're really going to have to go and challenge your thinking on these ones. I'm going to read this out because this is crazy small and I cannot for the life of me figure out how to make this bigger. A jar contains 4 black and 3 white balls. So here's 1, 2, 3. And these are perhaps the worst colors I could have possibly had in a word problem. And then there are 4. Okay, this looks like gray, but just imagine they're black. Okay, so that's what we got. And you reach into the jar and you pick 2 balls simultaneously. So at the same time, you take out 2. What is the probability that one is black and the other is white? Okay, so you got to think about what's going on here. What's really going on? So what's the probability that one is black and the other is white? Well, first off, this is a little bit misleading because when you pick things simultaneously, you're not really picking simultaneously. You're really picking one ball, then picking another, aren't you? So you got a couple things going on here. When you go and you pick that first ball, that one is black and the other is white. So you could choose. So if you have, at the end of the day, you're going to have, I don't like using that color. Sorry. At the end of the day, what are you going to have in your hand? I don't want that color either. Seriously. Where are my colors? There we go. Okay. So here you go. Here's my really bad hand. At the end of the day, what are you going to have in your hand to satisfy this question? You're going to have one black and you're going to have one white in your hand. So we're going to keep that idea. This looks like a tree. It doesn't look like a hand, does it? Okay, so here we go. Let's do the math. Let's do math now. So you take that first one. So what are the chances that you got a black? Well, it's 4 out of 7, isn't it? Yeah? Cool. And then you had to go and get a white. So 3 out of, and you took a black, right? So then you got a white, so 3 out of 6. So far, so good. And what are you going to do with those 2 things? This happens and then that happens. So you're going to have to go and multiply them, aren't you? So you're going to get 12 out of 42. Cool, easy peasy, right? That was easy. But wait, what if you had chosen a white first, though? Could you choose a white and then a black? Yeah. If you had done that, chose a white first, it would have been 3 out of 7. And then you would have chosen a black, but it'd be 4 out of 6. Okay. So you would have got 3 out of 7 and 4 out of 6. So what are you going to do with those 2? You're going to multiply it. And you get 12 out of 42. So there's 2 different ways that this could have occurred. You could have got black then white or white then black. Now, you have these 2 numbers here. So what do you do with those 2? Well, when you have something that is basically mutually exclusive, so you have things that are going to be mutually exclusive, 2 different ways really that were mutually exclusive. My writing is horrible. That really is going to say mutually exclusive. My tablet is not liking me. you can just go and add them together. So for this, you'd go 12 out of 42. I know this is kind of a weird one because they both end up being kind of the same, right? 12 out of 42. And you'd end up getting 24 out of 42. And if you're a good little student, then you go and you simplify that. And that'd be what, 12? I'm going to be like a kid. I do 12 out of 21. Then I do that again, divided by 2 again. Or by 3, I guess, right? And then 4 out of 7. So the chances of this happening is 4 out of 7. And if you want to think of, I was like, it's kind of fun. It's about 57%. So about 57%. So a little bit more tricky than just going and doing one straight up. You really had to think about what happens in this question. So a little bit of thinking and thinking about mutually exclusive ideas. These were mutually exclusive. We're going to get into an example where things are not mutually exclusive. But this would be kind of a tricky one for sure. Okay. Good work there. Let's go and get rid of that. Let's take a look at something else. Take a look at this one. Okay, well, here's one thing I just want to kind of talk about that typically, I'm going to give you some typical rules. Maybe I was going to call it a rule. I'm going to call them a typical guideline that usually helps kids. When you have and questions, things that say and, you just multiply. And when you have or questions, you typically add your different probabilities. Okay, so let's take this one. You're buying a new car with the following options to pick from. You have a 4-cylinder or a 6-cylinder car, so the 6 cylinders kind of go a little bit faster. And you have these different colors, red, green, blue, and white. So you have, there's like 2 options, and this one, there's like 4 different colors, right? What's the probability you get a 6-cylinder and a white car with a random selection? So how many ways could you do it? So how many ways could you get a 6-cylinder and a white car? So if you just think about it, again, you could use a tree diagram here. So you either get a 4 or a 6. And if you got a 4, then you have those colors. And if you got a 6, you have those colors. But I want to know specifically that I got a 6-cylinder and the color white. And if you look at that, there's only one way to do it. And how many different possibilities were there? Remember, the end of the branches tells you how many possibilities there were. So there are 1, 2, 3, 4, 5, 6, 7, 8. If you look at it just mathematically, so the first one, so probability of that is getting obviously 1 out of 2. And then you have to get a color, 1 white, so it's 1 out of 4. And you said the word and, so you kind of multiply those ones and you get 1 out of 8. So I give you a little bit of a guide, a little step guide and that kind of stuff. But I'll give you a tricky one now. This is really tricky. So that was kind of a question that you would definitely see. And here's your last one today. Well, this is I love this question because it seems so innocent at the start. But here we go. A die is rolled. So you got your 6-sided die. Easy peasy. 6 sides. What's the probability that the number is even or less than 4? So it's even or it's less than 4. Now I want to show this. I know I just want to show some theoretical stuff on this. So what's the probability that it's even? Well, how many ways could it be even? It could be a 2, a 4, or a 6. So 3 ways. And how many total ways are there? 6, so 3 out of 6. Or less than 4. So less than 4, it could be 1, 2, or 3. So less than 4. It could be 3 ways, right? And out of 6, 3. Now, the last slide, I just said if I saw the word or, I should go and multiply. Or sorry, I should go and add. Sorry, I should go and add when I see the word or. So if I went and added these two together, if I did that, 3 out of 6 plus 3 out of 6 is 6 out of 6. What? So that's 100%. That's guaranteed. If I roll a die, I say I'm guaranteed to get something that is less than 4 or even. Is that true? Is that true, everybody? Well, was there anything shared? Is there a shared outcome? Well, if there are shared outcomes, you must subtract. Does that make sense? You must subtract. So this is what I mean by that. Let's just go and list the outcomes. So the probability of even, there is what? A 2, a 4, or a 6. And less than 4 was 1, 2, and 3. Did they have anything that they shared? They did. They both shared a 2. So 1 out of 6 of the possibilities were shared. So what you really need to do here is do this. The probability of A plus the probability of B, subtract the probability of A or B. So what your math actually looks like is this. 3 out of 6 plus 3 out of 6, subtract 1 out of 6, and that's going to give you 5 out of 6. And that's your true probability. So be careful when you have shared outcomes. You do need to be subtracting them. And basically when you have or, you're going to do some adding there. All right, probability. Hope you enjoyed.
Thanks everybody for playing along with some probability. Hopefully you have a deck of cards, some dice, and you're going out and trying some experiments to see what really does happen. Until next time, go subscribe. Have a great day.